All right. So Bitcoin, I was saying, is the holy grail of digital currencies because it is trustless. And that's basically how it works. You have a QR code. You can send money to people. You don't have to do anything to receive money. This is an actual QR code with my actual Bitcoin address, so feel free to give it a try. And you don't need to trust anyone. And I will have to wait a bit before I can use the money you send me. And I do need to protect my private keys, so you do need good wallets. And the basis of Bitcoin, which I guess everyone knows about, are the blockchain, the UTXO, and the scripts. That's what makes Bitcoin work. So the blockchain, that's the easy part. Transactions are grouped into blocks, they're chained together, and the hash of a block has to be below a given target. UTXO, does everyone knows what UTXO means? Okay, so the UTXO, they're the coins in Bitcoin. UTXO means unspent transaction outputs. And it's a different model from the balance you have in other cryptocurrencies where there's a fixed account and you send money to an account and you get money out of an account. In Bitcoin, there are no fixed accounts. You have transactions that span the outputs of previous transactions. So it's like a chain of transactions that goes back to the first one that creates money. It's a coin-based transaction. And the outputs that have not been spent yet are the unspent transaction output, and they're the actual coins in Bitcoin. So to spend money, you need to spend something that has not been spent before. So when you have a block that comes in, it will use some of these UTXOs and create new ones. So new blocks change the UTXO set. And the scripts in Bitcoin, who doesn't know how scripting works in Bitcoin? Okay, so everyone knows how scripting works in Bitcoin, which is good. So Bitcoin has smart contracts. They're not maybe as smart as some others, but they're pretty smart too. And they set the rules for spending UTXOs. So basically, all this says that you can spend money that you own. That's what it's about. If you want to spend money, you need to have a UTXO on the blockchain, and you have to have the right to spend it. And the right is checked with the valid script. But Bitcoin doesn't scale, okay? Why? Because it's a global consensus system. Global consensus as in every node sees everything and checks everything and stores everything. So if you were all Bitcoin nodes and if I was to publish a transaction, everyone would see it and everyone would check that it's valid and everyone would store it. And all of you would need to agree on what is the state of the blockchain. That's global consensus. And it's really, really hard to achieve. And Bitcoin, I think, is one of the first systems of this kind. And that's why it's really hard to scale, because if you want to do 1,000 transactions per second, then everyone will have to see and store and validate 1,000 transactions per second. So is it possible to do something that is much faster? So what if we don't publish everything? And that's what Lightning is about. Basically, Lightning is a second layer on top of Bitcoin, where you don't publish transactions. It enables a different set of properties and trade-offs. You can have really cheap instant payments. It's very scalable. Basically, throughput is not limited, and it's still trustless. But you have different properties. And for example, you need to be online to receive money on Lightning, which is not the case in Bitcoin. But what is really important is it's a layer on top of Bitcoin. It doesn't exist without Bitcoin. It is not something you can just run on its own. It needs Bitcoin. It is Bitcoin. And basically, Lightning is built, the building blocks of Lightning are the payment channel and the HTLC payment model, a network of payment channels, and routing, which is a topic that is often a bit misunderstood. The basic building block of Lightning is the payment channel. So the payment channels have existed for a long time. I think the first ideas appeared in 2011. It was described more precisely in 2013, but the payment channels were not really usable because The first one, you had to open a channel to everyone you wanted to pay, so it's not really useful. Lightning is a bit different. But the idea of a payment channel is you open one with a non-chain transaction, you close it with a non-chain transaction, but everything that happens in between is not published. So you don't have the bottleneck of having to have your payments included into a block. And basically, that's what it looks like. Suppose Alice and Bob open a channel. Alice will publish a funding transaction on the blockchain. And Alice and Bob, at all time, will have what we call a commitment transaction that spends that funding ticks on the blockchain, and that just changes the way the money is sent to Alice and Bob. So if Alice opens the channel with 10 Bitcoin, the first transaction for Alice gives her back 10 Bitcoin, and the first transaction for Bob gives him back nothing. But if Alice wants to send, in this example, it's 7 Bitcoins to Bob, then the second commitment transaction for Alice has 3 Bitcoin for her and 7 for Bob. She's paid Bob 7 Bitcoins. And Alice and Bob will exchange messages that no one else needs to see to change how the funds are spread between them. So it's very fast. It doesn't touch anyone else. There's no need for a global consensus. And you can pay, Alice and Bob can pay each other millions of times, and it's almost instant. All it takes is they need to send messages and agree on how the balance is spread. And when they're happy, they can close the channel. And they can close the channel at any time, because in Lightning, you always have a valid signed commitment transaction. So even if Bob disappears, Alice can always publish her current commitment transaction and get her money back. So the trick of Lightning is, how do we update these commitment transactions to change the way the money from the blockchain is spent? A few things to notice. Why do you think the funding transaction sends money to Alice plus Bob? It's because it's called a multi-sig transaction. What it means is, if that transaction has to be spent, Alice and Bob have to sign it. If I have a channel with you, you can't spend the funding ticks without me knowing it, because I will have to sign the spending transaction. And in this case, if Alice broadcasts a funding transaction before Bob has signed a commit transaction that sends her back the money, what will happen is she's tied to Bob willing to sign her transaction. She has to ask him to do this. So the establishment of a channel requires Bob to sign a transaction that is not published. And if that transaction can be malleated, if the ID of that transaction changes, you have a problem. That's why SegWit really mattered for us. We had to wait till SegWit was ready, because without that fix, the creation of a channel becomes much harder. And in general, chaining transactions that are not published becomes much harder if the ID of your transaction can change before you without you knowing it. So that's why a fix for this was really important for us. And the payment model on Lightning is hashed, time-locked contract. Hashed because you are buying the pre-images of a hash. Does everyone know what a pre-image is? OK, so does everyone know what a hash function is? OK, so the pre-image is just the name for the input data to the hash function. So if you only have the hash value, it's impossible to guess the pre-image. It's really impossible. So if I give you a hash, the only way for you to find the pre-image is to wait for me to give you the pre-image. And it's really easy to express this in terms of scripts. And it's really easy to express this with other currencies and other scripted languages. So that I will give you money for a pre-image is something that is really easy to implement in Bitcoin script and other scripts. And basically, that's the basis of Lightning payments. There's a delay because if you haven't sent me the pre-image after a while, I need to get my money back. Otherwise, my money is stuck. So basically, a payment in Lightning is a payment hash, an amount, and a delay. If you give me the pre-image, I give you the money, and after a while, if you haven't given me anything, I get my money back. And that's what a Lightning payment looks like. A destination, an amount, and an expiry. So how does it work? Suppose Alice wants to buy something from Bob. Bob will create a random value, that's our pre-image, compute its hash, and tell Alice, okay, buy something for this amount and this payment hash. And this happens typically through a QR code. So Alice will propose a new payment to Bob. So Alice will change the commitment transaction to move 6 Bitcoin out of her output into a pending payment of 2 Bitcoins, and she will sign it. And Bob will will acknowledge the change. Bob will sign Alice's commitment transaction with the same 2 Bitcoins that are moved from her output to a pending payment. Alice will acknowledge the change. Alice and Bob will have a pending payment. Each will have in its valid commitment transaction a pending payment for 2 Bitcoins against the pre-image of H, and then Bob will sign the pre-image, and they will sign the commitment transactions again, and they will end up with a new commitment transaction where 2 Bitcoins have been moved from Alice's output to Bob's output. That's how payment works in one single channel. Basically, you change the way the money is balanced between the 2 peers in the channel. Why is this trustless? If we look at this, for example, Alice and Bob, they have several commitment transactions. They're all valid. So what is to stop one of them to say, okay, this one gave me more money than the one I have currently, so I should instead use this one? It is trustless because there's a concept of penalty transaction in Lightning. If you cheat and if you publish an old state, you risk losing everything. In each of your outputs, there's some kind of circuit breaker, something that says, if the other guy knows the secret, he will take everything. So it's actually very risky to publish an old state because they've been invalidated by you, because every time you move to a new state, you give out the revocation secrets for the previous state. So you have many, many commit transactions that are valid, but only the last one can be used safely. So that's what it looks like. This is Alice's commitment transaction. And you can see that Alice's outputs have a delay. 2A plus delay means when this is published, Alice has to wait before she can spend her outputs. But there are also a circuit breaker that sends money to B if Bob knows the revocation secrets. So if this transaction is published, Alice has to wait before she can spend her output. But if Bob knows the secret, he can spend these outputs right away. That's how you prevent people from cheating in Lightning. When you publish your transaction, you can't spend it for a while. And during that time, if the other guy knows your revocation secret, he will steal everything. He will get everything. For this to work, you need to monitor the blockchain. Basically, you know the funding transaction for your channels. So you have to watch the blockchain, watch every block, and okay, is a transaction in this block spending my funding transaction? And if it happens, you have to get the revocation secrets that you received and spend all the outputs. So you need to be active and monitor the blockchain. It's something you could delegate to a third party. We call it watchtowers. And basically, watchtowers in Lightning will monitor the blockchain for you. You will tell them, OK, if this happens, you have to publish the penalty transactions for me. And it makes it safe, and you don't have to do the monitoring yourself. But it's tricky to get right, because you don't want watchtowers to learn what you're doing. You want it to be private. So how do you design watchtowers to be efficient and yet learn nothing about what you're doing? Or even the channels they're watching. So a very clever idea that was proposed, I think, by Taj Drouin is you use the ID of the commitment transaction. You split in 2 parts. The first one is the index that you give to the watchtower. You tell it, look for transactions that start with that index. And the second part is the encryption key. So you give the watchtower as a blob that is encrypted with the second half of the commitment transaction. And when they see a transaction that starts with the first half. They use the second half to decrypt the blob you gave them, which contains your penalty transaction, and they publish it. This is really nice. It's really clever, but there's a problem. You need to store data. Basically, watchtowers need to store all the states, all the previous penalty transactions for all the states you had in your channel. So it's growing and growing and growing. So we don't have watchtowers yet, not because it's technically hard to do, but because it's hard to incentivize. And I think Patrick will talk about some changes that have been proposed for Lightning with L2, where you don't need to store all the previous states. All you need to store is the last one. So it makes running watchtowers much more sensible from a cost point of view. And when we have L2, we'll have easy to deploy watchtowers. But right now, there's an incentive problem. To close a channel, you have 3 ways. The good way is you agree with your peer, and you agree on a closing transaction, and you publish it, and that's it. That's when both parties are online. The bad way is your peer misbehaves, starts sending you garbage, or it's just not responding. So you have money that is stuck in the channel, and you can't use it. So you decide to publish your commitment transaction, your current one, and you need to wait a bit. That's the delay I was talking about when I explained the penalty transaction. So you need to wait typically 1 day before you get your money back. But you don't need inputs from your peers. So even if your peer is gone, you get your money back. And the ugly way is your peer is trying to cheat and publishes an old transaction. You have a window, typically 1 day. During that time, you can get the revocation secret for that transaction, create your penalty transaction, publish it, and you take all the money. One operational issue we've had on Lightning that is a bit of a pain is, what does publishable mean in Bitcoin? It means that the transaction you want to publish is spending a UTXO. That UTXO has not been spent yet. It means it is signed, but it also means it pays realistic fees on a Bitcoin blockchain. So since channels can be open for a long, long time, there are messages in Lightning to say, OK, update the on-chain fees. And this is a source of problem, because it may have happened to some of you, but when there's a spike in fees, and one of the nodes has not seen a spike yet, channels will get closed because peers don't agree on on-chain fees. So it's a bit of a problem that will be fixed with the upcoming version of the Lightning specifications, and that will be completely removed with L2. We won't have to worry about on-chain fees. But right now, we do have to worry about on-chain fees. We need to pay fees that are realistic, and it's sometimes a source of problems on Lightning. So that was the payment channel. But the really nice thing about Lightning is a network of payment channels, because payment channels have existed for a long time and nobody is using them because you need to open one to everyone. With Lightning, you have conditional payments. Alice pays Bob if and only if Bob pays Carol. And it works exactly the same way. Alice wants to buy something from Carol through Bob. Carol say, send me a payment for that payment hash for 2 Bitcoins. And Alice and Bob and Carol will use the same payment hash to create a pending payment on their own channels. So when Alice pays Carol in Lightning through Bob, what happens, in fact, is Alice pays Bob and Bob pays Carol. That's how it works. So in this example, they will do exactly the same pending payment and signed dance. Alice will create a pending payment with the same payment hash. Carol will send a pre-image to Bob. Bob will send a pre-image back to Alice, and they will update their balance. And what you can see is that Alice has paid Carol. Alice has less money, Carol has more money. On the left side, Bob has made 2 Bitcoin, and on the right side, he has paid 2 Bitcoin. So from Bob's point of view, it doesn't change anything. He still have the same amount of money. It's just spread differently between his channels. In practice, Bob will ask a small relay fee to relay payments. So Alice will pay just a bit more than 2 Bitcoins. She'll pay maybe 0.1% to have Bob relay a payment. And all this is still trustless. It's still using the same penalty transaction mechanism that you have on a single channel. What this means is, in the Lightning Network, if you can find a path to someone, you can pay them. So even if you open very few channels, like 2 or 3, if the network is connected enough, you can pay anyone. And it's instant, almost instant. So basically, if your network looks like this, Alice is somewhere on the left, Bob somewhere on the right. If Alice can find a path towards to Bob, she can pay Bob. And that's the really big change in Lightning compared to the old payment channels we had before. Routing in Lightning mixes 2 different ideas. The first one is how to find a route from Alice to Bob, and the second one is, once you have the route, how do you actually relay and send payments? So the first part, how to find a route, is not really part of Lightning. You can compute routes locally with your local view of the network. You can ask someone to do it for you. You can use whatever you want. This is not really part of the protocol. What is part of Lightning is, when you have the routes, how do you send money from A to C through B? And this is through an onion packet that works a bit like what you have in the Tor network. Basically, if I want to send something to D through A, B, and C, I will create a packet that is encrypted for D. And I will add an encryption layer for C, and again for B, and again for A. And when A gets the message, it will decrypt and remove its own layer and sees, OK, forward this to B, and forward what is remaining to B, and B will do the same, decrypt and remove its own encryption layer, and forward to C, and so on. So the way it works is, a node that is relaying a payment in Lightning knows the previous hop, the next hop, but it doesn't know where it comes from or where it's going to. So you have a pretty good privacy in Lightning. Of course, there are attacks on this. Obviously, if you control it's like in a Tor network, if you control the first node and the exit node, yes, you can correlate amounts and hashes, and you can guess who's doing what. But if you don't, all you know is there's a payment coming from this node, it's going to this node, but you don't know where it starts and where it stops. So there's a really good privacy in Lightning. There's one tiny problem right now is the pre-images will be the same. So the pre-image and the payment hash is the same along the route. This is something that will be changed. And pre-image will be blinded with a different blinding factor at each hop. So it will be much harder in the next version of Lightning to correlate payment hashes. So the way payments work on Lightning is you scan a payment request. It gives you an amount, a hash. You compute the route to the destination. And there are different types of wallets, but what we try to do is to do what we call full Lightning nodes, which is they are not remote controls for other nodes. They don't rely on custodial services. Everything is done locally. You compute your route locally. You create your onion packet locally, and you send it on a network. And destination sees your payment, sends back the pre-image, and you've paid. So what you have with Lightning is a project that is a bit different from most projects in crypto because it's an open source project that is not driven by a single company. There is no Lightning Incorporated or Lightning Limited. It's an open spec. There are open source implementations, and I think that's one of the reasons it works. It's because anyone can join, anyone can implement it. And you can start, for example, you have, if you read the specs, they're written like an RFC document. So they're very detailed. You have test vectors, you have descriptions of the low-level binary messages, of the transport layers, of the Bitcoin transaction you can use. And it's hard work, but just with the specs, you can implement Lightning. There's a Japanese team that implemented C++ Lightning nodes last year, I think. And they didn't read our code or Lightning Labs or Blockstreams. They just read the specs, the test vectors, and implemented Lightning. So that's quite an achievement. You have open source implementations in C, in Scala, which is a language that runs on a JVM, in Go, and C++, and Rust, and Python. And this is possible because since there is no global consensus, what you do with your peer has no impact on the rest of the network. In Bitcoin, there are a few alternate implementations of Bitcoin, but I think 99.9% of all nodes run Bitcoin Core, because if you have just a tiny mistake and if you don't do exactly the same as the other nodes, you're going to be forked off the network. It doesn't happen in Lightning. It's standard client-server system where your interactions with your peer have no impact on the other peers. So it's really easy to stop, upgrade, restart. It's really easy to run different implementations. From an upgrade point of view, it's much easier to work on Lightning than it is to work on Beacon Core. All these are open source. There are probably more to come. The Lightning network right now is 5,000 nodes, a bit more than 20,000 channels, and about $2 million in capacity. There's something that is very, very important and that most people don't notice. This is the public network. This is the network of channels that owners have chosen to make public. But it's much, much bigger. For example, nodes that do not relay payments are not announced publicly. So we have thousands of users of our mobile node that will not show up on a network because it doesn't make sense to announce a node that is on a mobile phone and is not going to relay payments. There are lots of terminal nodes that just receive payment but are not route payments, that are not on the public network map. So the Lightning network is actually much bigger than this, and it can be made really private. You can have your own private Lightning network of nodes that are not connected to the main graph and that nobody will see or hear about. You can even exchange node routing information like through email or otherwise, and nobody will know what's going on. So that's really important, just the last item. There's a lot of confusion on routing, limitations of routing on Lightning, but as it is today, with a public network of a few thousand nodes, it could serve millions of users, because typically users don't have to have public nodes and public channels, and merchants don't have to have public nodes and public channels. So there is no ceiling that we're close to hitting because of the limitations of routing. It would work with lots of users the way it is today. Okay? Okay.
Thank you very much.